Okay,
Okay,
it's
you're
now recording.
recording.
Yeah.
Okay, good. So let G be a reductive group over K, and K is going to be complete. Okay? Non-Archimedean with this discrete valuation. Okay? So we're going to take a chamber in the building associated to G. That's going to be a chamber. Uh, we're going to uh, consider a BT model. So BT, remember that BT means Burhat teach. And
Mm-hmm.
I'm going to use BT all the time. So a BT model of G associated to the stabilizer. Okay. GK. Notice that big K means the field. It's not the unramified, the maximal unramified extension. Okay. It's just the base field. Okay.
Mm-hmm.
And we're going to take, so I'm just copying what you wrote, your notation. This is your notation.
Yeah.
And so we're going to take the group of components associated to this chamber, which is by definition the KNR valued points of G, a certain definition. We don't care about the definitions at this time, no, the precise definition. Okay, but this is a gamma NR module. Okay, and we're going to take, and what is this one? This one is just by definition. I think I need. There may be a problem with the notation here. I think this is the subgroup generated by all these things, where F is a facet.
Yeah. Yeah.
Facet of the building. Okay. And we're going to define now phi of G without the subscript. This is going to be this thing. Okay, that's your notation.
Mm-hmm.
And so well, I'm not going to write the lemma because you don't give a complete proof. So I'm going to write conjecture. This is your lemma A to 8.
I haven't done a full proof of that.
Well, your proof, the proof that you sent me had some questions, contained some questions in it.
It's I have probably fixed it
Okay, you fix
meanwhile.
it later, but yeah, but the version that you sent me had some incomplete proof because there were
Mm,
some questions in it.
mm.
So I'm just going to call it a conjecture. But this is
Okay.
not a problem for what I'm trying to will explain. Okay, so
Okay.
it's just so please do not be offended if I only call it a conjecture and not a lemma. Okay. So it's not that I don't believe you. It's just that wait a minute. There's a problem here. This is I skipped something. This is 2-7. Okay, and so this is going to be the canonical map. The canonical map is an isomorphism.
Okay. Uh, yes. So mainly the issue with all this stuff is that when we get out the perfect residue field case, uh, there will be a lot of things that will not be obvious actually.
Right. Yeah, maybe in the perfect residue field case, there are still some things to be checked, right?
Mm, well, there is still a lot of thing to do, but
A lot of things to do.
it works way better than the general case.
Yeah, okay, but this is your conjecture, and maybe it's a theorem already. Maybe it's you maybe you proved it.
Okay.
At least in the perfect residue field case. Okay. But what this conjecture says is that uh, this group really does not depend on the chamber, the chosen chamber.
Yeah.
It is something that actually comes before BT theory. Okay, it says phi of G. Of course, the definition of phi of G still uses this group, which is defined this way.
Well,
So
actually, we can define this group without using BT theory. Just
yes,
because what we can also do to define this group is to take the subgroup generated by the images of all smooth fiberwise connected models of J. So it will
okay,
give the same group.
the same answer. And actually, all you mean all smooth connected models over the ring of integers, right?
Yeah,
Without choosing any chamber or
yeah,
any
exactly.
facet, nothing. So it seems that this object, here exists independently of BT theory.
Yeah,
Right? It's something attached to the reductive group G without even constructing the building associated to G. It's something, it's fundamental. Okay, that's one of your conjectures. Uh, and the other thing that one of the other conjecture that you have, or maybe you proved it already, this is lemma A28, that says that this is a functor.
yeah, I think it doesn't cause any problem.
There was no problem here.
Yeah, I think so.
Yeah, it's probably true. This is a functor. Okay, and there's the theorem, and this is probably true, independently of any conjectures, uh, that there exists a unique morphism. This is a Godwin's morphism. P of G that goes to pi 1 G I, and this is functorially in G. Okay, and this pi 1 G is the Borovoid algebraic fundamental group. Okay, I think I didn't do something that I
Uh,
should have done. Let's put more ink into these pens. So we're gonna take a break. Okay. So I hope you have time because this talk is going to last at least 1 hour. Okay, so you have enough room in your computer to record this for 1 hour?
uh, maybe we will have to stop just to so that I can get more space. I am not
Well,
quite
yeah. It doesn't matter. It doesn't matter. We can stop and have a break later because go to the bathroom, whatever. But and if necessary, we can have another talk tomorrow. Okay, if you find that this is becoming too long, we can have another talk tomorrow.
okay.
Oops. It's not good to bring ink from the office that is actually empty. Anyways, that was a mistake. I didn't check this, but I'll find a way. I think I have another bottle of ink there for the blue pen. So this one is gone. And this one still has something in it. Okay, so we're okay. We have the blue pen. So we have the blue pen for good. So that's excellent. So these little things are important, but I was busy with other things too, so I missed this ink thing. Yep, it should work. Okay, so this is what we agree on, that there's a morphism of gamma NR modules. Okay, this is the couplets.
Yeah,
And that's a morphism. It's not an isomorphism in general, it's just a morphism. That's all the
yeah.
theorem says, right?
So the whole issue is that in the perfect residue field case, it would be an isomorphism, but in the
Right.
general case,
We don't
it
know.
wouldn't be.
Yeah, it wouldn't be. There would be some defect that one has to understand.
Hmm.
Okay. All right. So that's page one. Now we're going to define. So we're going to define this morphism the way it is done in the KP book, the Kalesa-Prasad book. Okay. So I'm going to just review what the KP book says and how it defines this. And this is important because I have an alternative definition,
Hmm.
um, which is the one I want to show to you. So all this may seem like a waste of time, but it's not. So how do they do it? Now that's a Prasad definition of the Godwin's map. So we take a Z extension.
Yeah, so it's the first way of doing it.
Take a Z extension. Okay, and so that's going to be this extension. Okay, where Z is an induced torus. This thing should be working. I don't know why it's not. Yeah, I'll start working. And the derived group of H is simply connected. Okay,
Hmm.
that's what a Z extension is. So this is a particular type of torus. It's an induced torus, and this H in the middle is such that its derived group is simply connected. Okay, so it means there's no mu, there's no kernel.
Your camera is not showing very well the
You
whiteboard.
don't see it, you don't see very well the board.
Not very well. Oh, it's way better right now.
Way better, yeah, but I don't have black ink. So we may have to continue tomorrow with a different pen or something. Okay, but maybe it's not needed. Okay, so that's better, right?
Oh yeah, yeah,
That's
yeah.
way better. All right, so my notation is, I'm going to use this notation. In the KP book, they use D as in David, but I prefer this notation. Okay. Not red. All right. That's my dyslexia again. It's D there, the derived group. Just a quotient of H by the derived group. That's a toric part. Okay. And so then we define a kappa map that's associated to H, but regarded over this field, K and R. And that is just, and they define this, which in this case is the same because H has these properties. So this is just pi 1 of H toric part. This pi one of a torus. This is just the sheaf of co-characters of this guy, of the group of co-characters. Okay, that's so this they define it that way, and they do this on page 429. Okay, and then they use this extension to define it in general. Okay, so I'm going to skip some details because of I don't want to waste my ink. So there's some steps that I miss here, but you
I'm
know
not
them.
quite sure. Uh, uh, so what are you saying? So for H, how the map is defined? So I thought we try to so first we define the map for tori, and then we use the isomorphism. Uh, well, a nice correspondence with tori, and then we can construct the map for the case of H. So
Uh,
it's
yeah, maybe I did it the wrong way, but this is not important, okay? You know that this can be defined, and so I'm just gonna skip to the last part, which is that we have a map. The code morphism is defined usually by defining it first over this field, and then you restrict to G of K, and then you get the map from G of K to pi 1G. Okay,
yeah,
but the construction has to go. I mean, it goes. They construct the things over this field and then they push them down.
yeah.
Essentially, yeah, that's what they do. See, here we have the Galois group of K and R over K.
Mm.
Okay. All right, so that's the map. And the problem is, what is the kernel of this map? That's the couple maps, the way it's defined in the KP book.
Mm.
And well, one question is, what is the kernel? And so the kernel is, yeah, the kernel is the kernel of this map is G of K uh, O, and what is this? This is G of K. Let me see if I get the symbol right. Something like that. So here M0 is a minimal Levi subgroup, is a minimal Levy subgroup, is a minimal. So it's the Levy subgroup associated to
Yeah,
some
yeah, yeah.
parabolic subgroup, whatever. It's a minimal Levy subgroup of G.
So
And
that's what they said in their book.
yeah, this
Uh,
is page 431.
yeah. But it's always the same thing. It's that it works in the perfect reduced field case, but in general, yeah, we
In the
don't
perfect
really know.
residue,
It's kind of weird.
well, in the imperfect residue fields, it's more complicated, you mean?
Yeah, yeah. We
Yeah,
don't know
probably
actually
so.
that it would be that.
Well, but you can assume that we're working over, whenever I refer to KP book, assume that the residue field is always perfect, okay? Because in that book, some parts work for in general, but other parts work
Mm,
for perfect residue field. So I think it is safer to assume always that the residue field is perfect while I mention the book, okay?
mm,
All right, so, but what is this? This one is the image of this map, the simply connected cover, GK.
yeah,
That's a definition. And so that's page 2. Um, okay, so this is important. Okay, this map is important. I'm gonna call this map delta or of K. Okay, it's the K points of a certain map that goes from G tilde to G. That's a map of algebraic groups. That's the Deligne map, okay, defined by Deligne a long time ago. Okay, so we have that, and I'm going to skip some of the things that I wrote here because they are just taken from the book. So what I'm going to talk is, so I'm missing. I can send you. I'm going to scan these notes, and I'm going to send them to you by email. Okay.
Okay.
So the things that I'm skipping now, you will be able to read this later. Okay.
Okay.
All right. So I'm going to talk about an alternative approach without BT theory. It's not because I don't like BT theory. I like it very much. BT theory is very interesting, very nice, etc. Okay, but we already pointed out some time ago. Actually, you did that this group of components phi of G actually exists. It is associated to the reductive group G intrinsically without any need for the BT theory to
Mm.
define it. Okay. So what I'm saying is that there must be an alternative construction, even of the Kodwitz map, which does not go through BT theory. Of course, after we've defined it in a different way, it is always an interesting question to see how the map behaves when you take one of the integral models that are defined in BT theory using the chamber and the building and etc. You see? So there is a connection, but for the construction of the map itself, what I'm saying is that there is a different way to define it that does not use BT theory. Okay, so we're going to talk about complexes now. There exists a canonical morphism of complexes. So I'm going to talk about the category of bounded complexes, whose term. So these complexes will be bounded, and its terms will be sheaves of groups, sheaves of abelian groups on this side, the flat side. Okay,
Okay.
I'm going to discuss complexes of abelian sheaves on the flat side over the field K. And sometimes we're going to change K into something, into a ring, okay? So I think I'm gonna turn my air conditioning on. I hope it's not too noisy, because it's the summer here, it's hot.
Well, actually, I haven't heard it, so it
Excuse me?
wasn't that noisy.
So what's the morphism that I'm going to talk about? So I'm going to identify my group. I'm going to view it as a complex. This one, okay? So G, I'm going to identify it with a complex. This is the trivial group, and this is going to be in degree -1, and this is going to be in degree 0. Okay, and so there is a map to this complex. Okay, that's a two-term complex also. This one again is in degree -1, and this one is in degree 0. So this is a canonical map. This map delta was defined by Deligne a long time ago in a paper, okay? In this complex, this is not important for what we're going to talk, but this is a cross module, which means that the group G, there's an action of G on G tilde that's actually a conjugation action. So you take an element here and you can act on the derived group because the derived group, you can act on the derived group by conjugation because the
Mhm.
derived group is normal in
Yeah.
G. So you get an action on G, the derived group, but the derived group is a quotient of this guy, and the kernel is abelian. That's
Mm.
the mu. The kernel is
Yeah.
mu, the fundamental group. Okay, so you can define an action that's a cross module. It satisfies certain conditions to become a cross module. Okay, so that's number. And the center of G acts trivially. Of course, because it's a conjugation action, the center is commutes with everything. Okay, acts trivially. That's one condition. So the center acts trivially here. There's a second thing, a second condition or property that the group G, because this is a reductive, this is the same as the image of this map, which is actually the derived group. So it's the G is the image of the map times the center. This is just a canonical, a very well-known decomposition of any reductive group is a product, okay, of the derived, any reductive is the derived times the center. So that's one of the key
Mm.
properties. For instance, this is false, is the group is only pseudo-reductive. But for reductive groups, this is true.
Okay.
And the third condition is that this map, if I restrict this map to the centers, this is surjective. That map, the restriction to the centers is surjective. With all these three conditions, then these three conditions, 1 to 3, imply that the canonical map, there is a canonical map. There's a canonical map here. This is a quasi-isomorphism.
I don't understand why the map between the centers are subjective because
Oh, this map?
yeah,
Yeah, it follows from a theorem in this G3. It's not trivial.
because uh what I don't understand is that J tilde is a semi-simple, simply connected group.
Yes?
So the center is finite and
The, the center of G tilde?
yeah. Oh
Well, that can't be because then the center of G will be finite too, right? Because it's surjective.
yeah, so I don't understand.
Maybe there's a problem with my definition. Well, it doesn't mean anything. Oh, but this is subjective. Maybe I copied that wrong. Ah, damn, sorry. There's a mistake. I copied wrong. Okay,
Yeah,
that's it.
so that's way better.
Yeah, way better. Yeah, sorry. I wrote it right here, but I copied wrong. Okay, so it's the map induced from the center of G tilde to the center of yeah. This one is subjective. All right. Okay, that's better. Sorry, didn't read correctly. Okay, so this is subject. These three conditions imply that this map of complexes is a quasi-isomorphism. It means the kernel of this map is the same as the kernel of this map, and the co-kernel is the same as the co-kernel.
Well, you
Essentially,
still need to add the G there. The You haven't added the the EEG there in the.
What do you say? Sorry.
You haven't corrected the the map, the center.
I didn't correct the map. Oh, yes.
Okay.
Okay. But actually, this is right. The problem is that this is the wrong map. So,
Hmm.
okay, I define a new map. So
Okay.
this delta prime is fine. It's surjective. This one is not surjective.
But
Okay,
it's another map.
it is a different map.
Okay.
It's just a map that goes from the center of G tilde to the center of G. Okay, that was the confusion. Okay, but now this is a quasi-isomorphism. So this means the following. This is just a translation of the following fact that so this is a canonical exact sequence because the co-kernel of this map is the toric part and the kernel is mu. So all this is saying is that this sequence induces this sequence. Okay. And so these two maps have the same kernel and the same co-kernel. That's all it's saying.
Okay.
Okay, so so we have an isomorphism then. So this one, I can view it is an isomorphism in the bounded derived category. So these are just the complexes modulo homologies. Or when you invert, you can take the category of complexes, bounded complexes, you mod out, you localize the category, you mod out by all the quasi-isomorphisms.
Mm.
Okay. And so you get essentially that these are the same thing. So this G tilde is the same thing as this one. Okay, and so this cross module is just, and this center of G acts trivially here. So this is just a, there's no action. The action is trivial. So this is just a complex. It's a two-term complex of abelian groups. So this is an abelian cross module. So we forget about the cross modules forever now because we're going to do everything in an abelian sense. Okay. So therefore, corollary, there exists a morphism that goes from G to this. Yeah, and this morphism exists in the here. Okay, so take the group G, map it to this complex, use this isomorphism, and then you get this map. And so we're going to concentrate on this complex now, two-term complex. The good thing is that you can forget about the centers by using a generalization of a Z extension. So this is a concept due to Borovoy, a T resolution.
Yeah. So it's just weaker actually.
Yeah, I'm going to use T prime for reasons that will become apparent later. So this is just like a Z extension, and but this T prime is any K torus. It doesn't have to be induced. So arbitrary, but H still is the derived group of H is simply connected. So this H is an extension of its torus, namely this torus, I'm gonna call it R. This torus, so this H is an extension of this R by a simply connected group. So it's something that's easier to handle. Okay. Good. So I'm gonna take a break. I'm gonna go into the bathroom and I'll be right back.
Okay.
So. Okay, so we're here. So that's number 4. So I'm gonna include an example now. So have a T resolution. Example. Let T be a maximal torus. T be a maximal torus of G. And T prime, let's call it T tilde because it's going to be the inverse image of T. This is contained in G tilde. This is a maximal torus. There's a maximal torus also in G tilde.
Mhm.
Okay. And there exists a T resolution such that this R group is T, the torus I started with. So this is an example. So every time you have a maximal torus in G, you can create a T resolution like that. Okay, proposition. Any T resolution, as in here, induces a quasi-isomorphism. Okay, that's a proposition that's it's proven somewhere. I know where it is, but it's not important now. So what do we have? So in summary, there exists a morphism from G to this. This is a complex of tori.
Mhm.
Two-term complex of tori for every T resolution. If I start with any G, we thought that construct the T resolution, for instance, a Z extension, and I can define this map from G to this complex of tori. It's a natural definition. And of course, you can define the Vorovoy group by 1G. Vorovoy defines this using this example. He uses maximal tori.
Yeah.
He chooses the maximal torus in G, considers the pullback, and then takes a quotient. But actually, this definition does not depend on that. Actually, it depends on you can take any T resolution and consider the co-character, the map between the co-characters, and then this co-kernel is the pi 1G of Vorovoy.
Hmm.
For every, so this is, It means if I choose a different T resolution, I'm gonna get a canonical isomorphism or whatever. It's not canonical, but if you take two T resolutions, you're gonna almost find a third that maps to the given two, and then you find a big diagram where you show that this thing does not depend on the T
Yeah,
resolution,
yeah, yeah.
actually, modulo isomorphism. It's something attached canonically to the group G, and in particular, you can choose this particular T resolution to define it. So you can, if you like, you can write this. For any maximal torus of G, where T tilde is the pullback.
Each
So,
time I discuss with researchers about this Borovoi group, they always feel like this object is kind of weird. Like Borovoi defines it just for its formulas because it feels nice, but we don't really understand what there is behind this thing.
well, probably Borovoy does it with the maximal torus, right? And he works over a field of characteristic zero or something, right?
Yeah,
Yeah, but this can be done for any base scheme. If you take,
yeah,
well, except for the weird ones, you take a nice base scheme, like take as local Noetherian regular or geometrical unibranch. Regular is too much,
yeah.
maybe, yeah, or normal, and then you can define a reductive group scheme over S, and then you can define the pi 1G and all that. But of course, the point here is that we're working with a reductive group over K, and we want to talk about Neron models
Mm,
or integral models that will not, some fibers of which will not be reductive.
mm,
So it's, the usefulness of the generalization is not so great because not every group G over K extends to a reductive group over a Dedekind base. There will be some weird fibers. So that's why we want to talk about the Neron model. So what's the problem here? Problem. This is the fundamental problem that I wanted to talk to you about today. What time is it? It's almost 1 hour. Okay, so maybe we should continue tomorrow. We finish 1 hour, and you send me another link tomorrow. We do the same thing tomorrow. I'll have better pens, and maybe I'll use my phone so that you can see the whole board. All right.
yes.
Now,
Uh,
what's the problem? That's a basic problem.
mm,
Define a Neron model of that complex. Define a Neron model of this complex. When your G, so that, this definition should be such that when G is a torus, then this one is zero, this one is the same as G. You get a torus here, and you go back, you end back, you recover the Neron model of a torus. And actually, perhaps we should not focus on the Neron model, but define an integral model. Maybe not the Neron, but in particular the Neron model. Define an integral model of that complex. So how to do that? So call it, I'm gonna call it this way, okay? It's an ugly name, but I have no alternative now. That's the name I chose. Call it that. So how to define that? And also question, once you define this, um, then the question is then to investigate, uh, if this map, investigate if this map, let's call it that symbol. Investigate if this map, this is a map of complexes over K. So it's not, this is happening on the genetic fiber of your sub4 model that you want to find. So this is genetic fiber. So investigate if this extends, in this particular map, I'm not saying every smooth morphism extends to, because then I would be defining the Neron model and maybe it doesn't exist, or whatever. But then investigate if this map extends to an O morphism, where O is the ring of integers of K. So investigate if it extends for some integral model. Integral models G. For instance, the ones that you find via PT theory. Okay. Then investigate if this map on the genetic fiber extends to a map between the familiar BT integral models that you find in BT theory, whether you get a map like that. And so the problem, but the essential problem is to define that. If instead of a complex of, so I'm not going to call it T prime R, I'm just going to call it T1, T2. If instead of a complex, a two-term complex of tori, if instead of that we consider a Deligne one motive, what is a Deligne one motive? Well, it's similar to this. But this is a lattice. It's not a torus. And this is a semi-abelian variety. Okay, so it's not the same situation, because here we have a different situation, because this is a complex of two tori. And this is a different complex. Here we have a lattice, which means it's the dual of a torus. And here we have a semi-abelian variety. But for these one motives, Suzuki defined a Neron model of this one motive. Suzuki defined a Neron model of this complex, two-term complex. And what I can show, not today, maybe tomorrow or some other day that we have a second meeting, this definition can be extended to get an Neron model of a complex of tori like this one. I have the details here, but perhaps we could stop now.
As you wish, actually, I have time. Not,
Yeah, but it's 1 hour, and you have already recorded 1 hour, and my pants are dying.
Oh,
Okay, that's the one problem. Let me see if I can keep going for a few minutes. Okay, I'll keep going until the ink gives way. Okay.
okay.
Okay, until you cannot see the board anymore, then at that time we stop. Okay, so, but I'm going to define the Neron model of a complex of tori. Well, why is this important? Because then I can you know, what I have explained. I can extend uh, the map of the generic fiber, and of course, I will define this. And in the next talk, which could be after I'm back from my vacation in the middle of February, then I can define in the middle of February. I can define the group of components of this
Mm.
Neron model, and then I can get a new definition or a new version of the Cogwitz map, but for any G, any group G, any reductive group. In the case of a torus, it will go back to Bitam's map. It will be, but there are some steps to do because now I will define the Neron model. Next time I'll define the identity, the group of components, and then one has to worry about duality theorems because
Mm.
now I'm going to work with a two-term complex like this where CI is either a K-torus or a lattice. So what I'm doing is I'm creating a new category that is closed under duality because if I start with the complexes of tori, I can define maybe I should write something like the dual. So I can pass from a two-term complex of tori, I can pass to a two-term complex of lattices.
Mm.
So here I have the characters of T2 map into the characters of T1. Okay, so that's the dual, and so I'm considering a category that is closed in the duality. This one is closed in the duality. You take the dual of this one, it gives you another lattice, which will be the group of characters of the toric part of this guy, and then
Mm.
you can get there's another semi-abelian variety that is not G, is a different semi-abelian variety, but the category one modus is also closed under duality, and
Mm.
I'm now going to work on this category that will be closed in the duality. So I have to define a Neron model. So I'm going to define a Neron model of either a two-term complex of tori or a two-term complex of lattices. So it works in both cases.
Mhm.
Okay. Okay, so I have this is page 6. Where's page 5? Okay, no, that's okay. Okay, so oh, this is just what I said there. 7, page 7 is the one I need. So let X be an irreducible Dedekind scheme. So I'm going to the construction works over any Dedekind scheme. So I can define the Neron model in the local case and also the global case. Actually,
Mm.
I'm not the one who does it. Suzuki did. So what I'm going to discuss here are his ideas. His ideas adapted to this case, which he does not consider. Okay, he focuses on one motives, but it's the same ideas. Let X be a reducible Dedekind scheme with fraction field or field function. Fraction field K can be any field, imperfect, maybe not a valued field, any field. Irreducible Dedekind scheme with fraction field K. And I'm going to take U. I'm going to define U it will be either the spectrum of K or a dense open subscheme of X. Of course, in the local case, this one will be a particular case of this one in the local case,
Yeah.
because in the local case you have only 2 points. This one is open, and you take the closure, you get everything. You know, but this is more general. Okay, so let J be the map. So this J is the inclusion of U into X, but we're going to extend it to a morphism of sites. So what site is this? This is the site of all schemes smooth over U with the smooth topology, or
Yeah.
equivalently the étale topology. Okay? You can, so you have this map of sites. Now let C be a bounded. So these are actually, this will be a complex of tori or lattices. So these are smooth and separated group schemes. So actually they belong to the category that I'm going to call it SM over U. These are the category of smooth, separated group schemes. Okay? Which is, of course, this maps into the category of all complexes, bounded complexes of sheaves of groups on this. These are, you know, a subcategory or whatever, because here the represented objects are not only sheaves or groups, but actually representable, and they are represented by smooth, separated group schemes. It's a smaller thing. Okay, but C1 can be, CI can be either a torus or a lattice. So in both cases. Okay. I have an example here that I will skip because I will send you a photocopy of this, okay? So let C of U be the category of these complexes. The morphisms between two of these are the canonical ones. I mean, C1 to C2 maps to C1 prime, C2 prime if you have a commutative diagram. Okay. The category of these complexes, let V over U be an any finite étale covering. Of course, I'm going to choose a particular one that splits one of the components. Here. But this definition works for any. V over U finite étale covering. 7. Okay, so consider now I can use 0 because everything is commutative. Shit. I need a notation. This is the same notation as Suzuki's, okay? I don't like it, but since I'm copying him, I can copy his notation too. So I pick a finite étale covering, now define C1 V. That's an ugly notation, okay, sorry. but this is just the Veil restriction.
Oh.
Yeah, it's an ugly notation. Yeah, but it's the Veil restrict. So you take the C1, that's defined over U. You base change to V and then pull back, pull down with Veil restriction. So that's C1V. Okay. The reason why he does this is it will be clear later. So now we consider, of course, this C1 maps into the Veil restrictions,
Mm-hmm.
and we're going to call the quotient ouch. So C1 is not C1V, it's C1/V because it's the quotient. Okay, it is not my notation. Sorry about that. And so we're going to call this map. This is an injection theta as a monomorphism. I mean, closed immersion, a closed immersion. C1 and 2. But here I have my delta. And I take the push out, which I'm going to call this. Of course, here we have C1, same thing. This is a push out.
Okay.
Okay. Define now C of V, not C1. C, the whole complex. So I'm going to take this map. Okay, delta bar. I'm going to take this map. So this complex. And it lives in here too. But notice, well, in Suzuki's case, this is not going to be the lean one motive because even if this is a lattice, this might not be because it will
I
be an
think there is an
extension of
issue
this.
with your notations because
What? The
your
notation is ugly?
your delta bar maps to C1 brackets V for
Oh,
above, but below
sorry.
your
There is an error here. That's it.
okay, and
That's the error.
so in your definition, okay,
That's the
okay, so,
definition. This is by it's a name. This is so this object is the push out.
yeah.
All right, and so I just call it since this pushes out into C2, I'll call it C2 square brackets, not to confuse with some version of this.
Yeah, it's
Okay.
not necessarily the definition we gave.
Well, Suzuki uses a round parenthesis, but that's confusing. That's why I use a bracket.
Yeah.
Okay, this is a push out. And in the case of one motive, this is not going to be a one motive because it's going to be a semi-abelian. All right, and this is going to be a lattice. So it's going to be some sheaf, an extension of the
Mm.
semi-abelian. It's going to be an algebraic group, but it's going to be an extension of a semi-abelian variety by lattice, which is not a finite type, it's locally finite type. So,
Mm.
but in this case, since this is either a torus or a lattice,
Mm-hmm.
this is going to be, well, this is also either, because this is going to be a quotient of this. So if this is a torus, a quasi-trivial torus, or quasi-split, the quotient of a torus by a torus, this is a torus. And if
Okay.
this is
Yeah.
a lattice, these are lattices, this is also a lattice. So
Mm.
here you get an extension, either an extension of two tori, which is a torus, or
Yeah.
an extension of two lattices, which is a lattice. So
Yeah.
we're not leaving the category, which is not what happens in the case of one mode. Okay,
Mm.
but Suzuki doesn't care because he works here or here. Okay, so this is a new object. So why is he doing this? Okay. So you get this. If the attack cover that I choose trivializes either the torus or the lattice, then you get this theorem. In the case of a lattice, this was proven by Suzuki in his proposition 2.8. And if C1 is a torus, then this is proposition 4.2.2 in Brandt's thesis.
Yeah.
Okay, so this works in both cases, lattices or tori. And so with this condition,
Yeah,
notice
because
that
it's just the push forward of a quasi-split torus.
yeah, you take push forward of either a quasi-split lattice or a quasi-split torus, and then this is
Yeah.
for the smooth topology, of course. Okay, so you get that vanishing. Okay, so what is this good for? Definition. The Neron model of my complex, according to V, is by definition this object. And this belongs to this is I don't maybe I'm not sure if this is actually
Hmm?
representable. Maybe it is
Uh,
representable by an object here. Remember that the objects here are smooth separated group schemes over X.
well,
So
for
I'm
Tora,
just
it's
saying that
just neural models.
yeah. This is the Neron model of the lattice or a torus. In the case of a torus, this is we know what this is. You know, it represents it's representable by the Neron model of the
Mm.
torus. And this one is also a torus when we are or this one is a lattice and this one is also a lattice, and one can define the Neron model of a lattice essentially by this object. Okay. So, but Suzuki worries about that in his paper, and I have not included the details. But this is a contravariant functor on V. For any given C, I get lots of these things because I can change the covering. I can choose actually two different coverings that split the thing, you know? So,
Mm.
so it is not clear that how canonical this is. That's not clear. Proposition. Proposition. We have a morphism. This is the derived R. Okay, derived R of this is a C of V is a complex. You take the
Mhm.
push forward of this complex, take the R, this is an object of the derived category. This is isomorphic to just this. Because why? Because this is an equality. So this complex is quasi-isomorphic to this complex. Because the third complex is an identity, you know. So the cohomology of this guy is trivial.
Oh,
So that these two are, and that's why so you see, this CV lives here. This is CV. This is the left here, the left. But because of this fact that you have an equality, this is quasi-isomorphic to the object that you care. So
okay. So it
right,
doesn't
so
depend on V, actually.
doesn't so it's independent of V. Anyways, this map induces an isomorphism. Truncation. Truncation, you stop at zero because this is the complex in terms in degrees minus 1 and 0. So you don't need the whole thing. This is infinite. You just take the translation, you stop at zero. So this is gonna have a -1 and a zero.
Okay.
So that's a proposition in Suzuki's paper. Of course, he does it for one motives, but I do it for complexes of either tori or lattices because that's what we care about. Last page, last. It's not even a full page. Well, I knew this was going to take at least an hour. So that's why we should have a second meeting when I'm back. I'll explain why. Because I need 2 more weeks to keep reading Suzuki's paper. Because he cites himself. He cites, he says, see my paper on the État rational site. Okay. And the État rational site he uses that in order to establish the duality theorem that leads to Bitan's formula, recovers Bitan's formula. But that I'm certain that his definition of the entire rational site, which is actually due to Cato, I'm certain that that's not the right definition to consider if your residue field is imperfect. Okay, but I have to keep reading his work in order to make sense of all this and see how it would extend to the imperfect residue field case, which is what we care about. Proposition, okay? Well, it says here that everything, let me just summarize it. Everything is independent of V up to isomorphisms. Okay, so which is what you guessed here,
Yeah.
It does not depend on which V you take. You take two different V's, you get a diagram that commutes, a commutative diagram, and then you get an isomorphism at the level of the derived category. So if we view things in the derived category, the V does not matter because there are always isomorphisms, which means that the cohomology sheaves of all these complexes are isomorphic to each other, independently of V. That's what it says. Definition. I have a functor. I have defined a functor that goes from this category to the bounded category of smooth separated group schemes over X. So I'm finding a model over X. Okay, starting with you could be either spec K or some fattening of spec K, something wider. Okay, some spread out. You know? And this functor is defined this way. To C, I just associate this Neron model that depends on V, but it's actually independent of V here. So you get an object for a suitable splitting for any V, and actually for any V. But in order to compute this, you choose a V that splits the C1, because then you get this theorem that R1J lower star of CV is zero. Okay, so you can compute this
Mm.
in theory, at least. So N of C is the Neron model or the integral model. Yeah, actually, Neron. The Neron model of this C. So I have to find the Neron model of a two-term complex of tori or lattices. Okay. And
So if we wanted to work with other integral models than the norm model in our construction, we would have used other things than the push forward by J.
well, but yeah. So you mean you want to make the same construction for other models, not necessarily the Neron model,
Yeah.
right?
So instead of taking the push forward, we would have taken other things, I guess.
Yeah, yeah, but you have to think about it. I have to think about it. I don't know how to do it. Anyways, you can always, uh, given the Neron model of a torus, you can always consider the identity component of that, and you can
Yeah.
consider the connected, but you see, this should wait until I can define to you in our next talk. I
Mm,
will define to you the identity component of the Neron model, imitating what Suzuki does,
mm,
and I will define the group of the complex of components, okay, and then the coupled maps in that generality. So for any reductive group G, okay, but this has to wait until I'm still reading.
mm.
So this is almost the end. So I'm just gonna send you a photocopy, a scan of my notes, okay? The things that I discussed here today. But what's the corollary of all this? That Suzuki's ideas can be adapted to this context, and they work, okay? At least in the perfect residue field case, one gets duality theorems. Now,
Yeah,
Bitan.
that's kind of funny because it's like neural models. At the beginning, it was for a billion varieties, and actually, there is some ideas that can be still used for affine groups.
For a billion, okay, you mean the normal model was originally defined for a billion varieties, and now it's defined for almost anything.
Yeah,
Well, yeah, but
it's kind
this
of.
is not. But look, these complexes are just very specific. They are complexes of tori or of lattices, and actually, well, this has never been done before. No one has defined these neural models of complexes, but uh, in the work of Demarche, he considers these objects over any base, but he assumes that these are either tori or actually I do too. So what I'm saying is that when I have a complexes over any S over a base S, very general, it's a scheme. So these are either S tori or S lattices over a scheme S. And if S is, for instance, a Dedekind scheme of arithmetic interest, there are there are duality theorems that connect class sets and class groups of reductive groups, and also Tay-Shafarevich group of looking at the Tay-Shafarevich group is defined on the generic fiber, but actually it's a global object. So Demarche has discussed these things, but in this case, let's say that Demarche has worked with the Neron models that I'm defining here. He has worked with the Neron models, but in the case of good reduction everywhere. Okay? And so what I'm doing here, following Suzuki, is defining a Neron model independently of the fact that the of good reduction everywhere. So this one will
Yeah,
be,
yeah, yeah.
understand that there will be a complex, but it will have bad fibers. I mean,
Mm,
some fiber will be multiplicative, some will be additive, whatever.
yeah.
But it's a, I think this is the way to go. Because why? Because actually Suzuki mentioned this. See, Suzuki says my theorems in this paper for one motives. Okay, so remember that he works with one motives. He says, well, I can specialize and consider zero in this a torus. When I apply my theorems to this case, my duality theorems, I recover the uh, the Bertapel Gonzalez-Aviles um, formula. So Vitan's formula. So
Mm,
Suzuki says, in the particular case that my Deligne one motive is of this type, then my duality theorems yield back this formula, which is due to Bertapel and Gonzalez-Aviles, but we know
uh,
that this formula is really due to Vitan. That's Vitan's
yeah.
formula.
So
Okay.
he actually said explicitly that there was this isomorphism. Oh.
Yeah. I mean, Suzuki says in this paper, I generalized the duality theorem of Gonzalez-Aviles, and because this is a duality theorem, because this is saying that the
Mm,
dual, he's saying that the dual of this is the fixed points of the group of
mm,
characters.
mm,
See? So this is a duality theorem because here you have a torus, here you have the
mm,
co-characters, which is,
mm.
it's a duality theorem, really.
Uh, but
So,
his
so
paper is from which year? When does he
uh,
published
tw-
his?
2018 maybe, 5 years
Oh,
ago,
okay.
right?
Okay, so it's very new actually.
Yeah. Actually, no one has paid any attention to Suzuki's paper until we
Wow.
have. Okay, it's not universally cited. Okay, because mathematics moves slowly.
Mm,
Eventually someone will realize, oh, Suzuki's work is important. Okay, we're realizing that now. Okay,
mm,
so this paper by Suzuki is important because because of the ideas contained therein, and also because we can imitate his methods to get at the reductive groups, and define Cowitz's map in a different manner, but he mentions explicitly this in his paper. He says, what I'll do here is better what Gonzalez-Aviles and Picat did. Well, he doesn't put it that way, but yeah, but I agree with him. What he does is better than what we do or what Bitan does. It's more general, but he does it for one motives, and so it does. His ideas do not specialize to this case. Okay, when we have two tori here, and in the two tori case, when you have T1 to T2, that's important because you get to the reductive group G.
Mm,
To any G, you can attach a two-term complex of tori. The Marsh has already done that. He has realized that. Yeah, but he's only worked in the good reduction case.
yeah.
So this is more general. Okay, so this is what I'm saying. So this is not just an artificial construction. This is important. This works, but it requires a lot of effort. For instance, anyone trying to work these things out must be familiar with the derived category language. Okay, and so so this is what we should do. If you are interested in this stuff, you should. While I'm reading the rest of Suzuki's paper and other papers over these 2 weeks until our next meeting, you have to take this Kashiwara Shapira book and read all the chapters that deal with the derived category.
Mm,
Okay? So that's what you have to do. I'm sure that this is the right way to go. And the problem with Suzuki's is that his theorems his duality theorems only work in the perfect residue field case too.
yeah.
He doesn't do the imperfect residue field case. My guess now, at this time today,
Mm,
my guess is because he uses these Étale rational sites that Cato invented that are very well suited for the perfect residue field case. But in the imperfect residue field case, one has to modify things, maybe a lot. Okay. But even if we decide or you decide to work in the perfect residue field case only, of course you're not going to get anything new here.
mm,
But you might get something new here because the duality theorems that Suzuki found for that general case over the perfect residue field case, you can do this, you can do that for this. For these complexes of tori or complexes of lattices attached to a reductive group where the residue field still perfect, but your theorems will be versions or different versions of Suzuki's theorem. So it will still be an interesting research paper that must be published, should be published. The imperfect residue field case takes longer because it's more difficult, which we know it is. Okay, but uh, if you don't do the perfect residue field case, you have no hope of doing the more difficult case
mm.
of, of the imperfect residue field case. So So you'd better work out the duality theorems for this one in the perfect residual field case, but taking complexes, two-term complexes of tori, which is missing because Suzuki didn't do it. DeMarche did it only for the good reduction case. Okay, he didn't. DeMarche never mentions Neron models of this stuff because everything for him is defined. He has S tori, S lattices. He doesn't worry about bad fibers.
It's
Okay.
an issue that we have in the literature where people are always working with reductive groups over the whole basis. So
Over the whole base. Yeah.
yeah, so it's
He.
it's like when we want to define Flask resolutions, we take
Yeah.
a multiplicative reduction torus, but
Yes.
we want something more general sometimes.
Yeah. And we want to admit bad reduction points.
Yeah.
And this is the way to do it. Then Neuron model. Okay. So I have defined for you the Neron model of a complex, two-term complex. I did part of your job. Okay. So I'm gonna send you my notes. I'm gonna scan the notes and send them to you today. In the meantime, I'll keep reading, but you should read about derived categories, the Shapira, the Shapira book, on
Mm,
category theory, whatever. Read, get acquainted with the derived category language because that's the way to go. If you don't believe me, ask Philippe. Philippe Gilles knows, understand this stuff. Okay, you can show the video to him or explain what we. Maybe he doesn't have the time, but you can explain to him what
mm.
we, or maybe show him my notes, whatever. But you guys decide. I'll keep reading this stuff because I'm interested. I don't have the time to do it myself because I'm working on other stuff. I need help. This should be done. All this should be done by someone. But I'm busy doing other things now. I cannot do this. So I need someone young with energy to take up this problem and carry the weight and do it the right way and finally work with bad fibers at least in the perfect residual field case. But that would be something new, worth including in any good thesis. Okay, because Suzuki didn't do it, and DeMarche didn't do it, even in the perfect residual field case. So if you do that, then you'll have a good theorem, a good results, and also you'll be preparing the way to tackle the more complicated imperfect residual field case later. Okay, that's what I'm saying. Okay, water. I need water. Okay, we finished this now. Next time, I'll promise I'll have better pens. Next time, we will see the whole board, and we can have another one of these next month, like the 20th of February, something like that. Whenever you want. In the
Okay.
meantime, I'll keep reading Suzuki. He's a very good mathematician, young mathematician. He writes good stuff. So he writes things that are better than mine, of course. But that's the way of life. Young people have more energy, better ideas, and all that. Okay, I'm gonna scan this. I'm gonna ask my secretary to scan these for you. Okay, these pages.
Okay.
Okay, so we stop until next time. Okay.
Okay.
I hope you discuss this with Philippe and you decide whether or not you want to get into this problem. You want to, read about derived categories. Uh, you cannot escape them. You'll eventually have to.